In this lecture, it's going to be a little bit shorter. We're going to take a look at power and an analytical approach to understanding the relationship between power and work. And so when we think about power, power is simply defined as the rate of performing work. And when you look at the word rate, we're talking about a time rate in which work is performed. And so examining the term work, we are referring to an object that is in motion. And this is a very important characteristic when it comes to power because it relates to not just an energy change, but the rate at which energy is changing. And as an equation, power is equal to the work performed that we step through in terms of how to quantify work performed as a force applied against an object that moves across a particular distance, divided by the time it takes to perform that work or the time taken for that object to move that specified distance. And so in terms of the units for power, as we know that the work performed is a Newton meter divided by time, and another expression for Newton meter is the joule, and so 1 joule per second is equal to 1 watt, which is a common unit, the common unit that is often used when referring to the generation of power. And this equation can be derived slightly differently, in which power can be computed as the applied force times the velocity of the object in motion. And so if we take a look at two individuals here we see the individual on your right will complete the running of a prescribed distance in 9.7 seconds. This person doesn't seem to be in as much of a hurry, completes the same distance. Both are moving across 100 meters. Obviously, they have to perform some level of mechanical work, and that work has to be performed against body mass of 85 kilograms. Now, because they're both completing the same distance and they have the same mass, the amount of work performed is going to be the same between these two individuals. But looking at the pictures, obviously it's not going to be the same. So in terms of power, the person on the right is completing the same amount of work in a much shorter period of time than the person who doesn't appear to be in much of a hurry. So in this case, the person on the right is generating a significantly greater amount of power than the person on the right, slightly more than 3 times the amount of power. So the next two slides will detail the analytical relationship between power and work. And so if we wish to obtain a value for mechanical work from power, we express power in watts as a function of time. And if power is held at a constant rate over an interval of time, we just simply multiply power by time, and that will give us a value for work. And so what we're basically doing here is calculating the area under the curve. In this particular case, the curve happens to be a straight line. And so in this case, we're calculating average power because our delta t, our change in time here, is a fairly wide period of time. Now in this case, power is held constant, so it's not changing, so a power calculation at the end is going to be the same as the power calculation at the beginning. And so it's just simply the amount of work performed per unit time. And so in terms of work, work is going to be equal to power times the change in time. Now we see on the bottom here, we see we're plotting work against time. In this case, now we don't have a consistent level of work. This is something that is going to be a little bit more reflective of human biomechanics. And so what we ought to do here is to determine power, we know that based on the equation that power is equal to work divided by time. And so what we need to do here is we're not going after an area calculation, we're going after a slope calculation, which is basically the rise over the run in this case. But when you take a look at this, you see a bit of a problem because we don't have a constant function, we don't have a constant profile for work, and it's very nonlinear throughout the entirety of this time. So in order to calculate power, what we need to do is calculate power over very small intervals of time. And so instead of using a delta t or delta time, we use the letter D for time, indicating a very, very, very small interval of time. In fact, this interval of time is considered to be infinitesimally small. This is an interval that keeps getting smaller and smaller, but never, ever achieves a value of 0. And so what we're in doing this, we're able to calculate something called an instantaneous slope that is applicable at only this infinitesimally small interval in time. We would then move this very small interval of time to the next interval, calculate another slope, and repeat that throughout. And as you follow through the red line, you'll see that the slope changes direction continuously all the way through, as well as changing the magnitude of that slope. So at the very bottom of this trough here, of this concave portion, we would calculate a slope of 0. At the very top, we would calculate a slope of 0. And so that is a joule per second, which is our measure of watts. And so another expression for power is equal to the what's called the first time derivative of work. So this approach here, using this notation, will give us instantaneous measures of power, whereas the equation at the very top is used over larger intervals of time, will give us average powers over those particular intervals. Now, in terms of attempting to derive work from power, the key element here is expressing these profiles or these data with respect to time. So here we have a power profile as a function of time. We have our very small interval of time, and we can calculate a rate of power generation. So once again here, we do not have a constant level of power. It varies throughout this period of time, which is very characteristic of many movements. But if we follow the same approach, if we wish to calculate the instantaneous slope of the power time curve, or the power time function, our final units will be watts per second. This is not a very common unit that's used in biomechanics, but dimensionally, it is certainly something that we can calculate. But to go in the opposite direction from a slope is to calculate the area under the curve. And so by calculating the area under the curve, we're essentially removing the time element to it, and we get a measure of work. Now, to calculate work here and determining the area, we saw this in an earlier lecture, that we're dealing with a geometric shape that is not simple. It's a very complex looking type of shape, but work is still represented as the area under this curve. So to do this, we would calculate the area under the curve starting at an initial point in time and a final point in time. This final point in time could be a little bit earlier. The initial time could be a little bit later, but we're selecting the beginning and end as we see this profile. And to calculate the work, that is the definite integral of power over infinitesimally small intervals of time between time 1 and time 2. So to provide an overview of this relationship of work and power. We establish that work is equal to force times a distance. This is, of course, a scalar quantity, which does not have direction. Power is the time rate of work performed, and if we expand that, that will be equal to force times the distance per unit time, which is a force times velocity in terms of power. So we can calculate power if we know how much work was performed, we know the interval of time, we can compute the power. If we have an indication of the applied force and the velocity of that object, that will yield the same values if we had these data as opposed to these data available to us. And so this is the approach we would take in the linear case. Now when we're dealing with rotating systems, we calculate work according to the same approach, except that instead of a force is replaced by a moment of force. And where we talk about a linear distance, we talk about a change in angle. So as we had statics and dynamics, so a static situation, there was no change in angle, but in dynamics there is a change in angle that will allow us to calculate the amount of work performed. And so in doing so, into translating this to calculating power, once again is equal to the amount of work per unit time in the same manner as we had in the linear case, except that in this case we have a moment of force rather than a force. We have a particular angle through which that rotating segment has moved through per unit time, and when we take the change in angle divided by the change in time, this is not a single angle, there is a change in angle, that's going to be equal to omega, which is our angular velocity. So although the symbols here are different, the symbols represent the same quantities. So quick video here. This ends this lecture on the relationship, the analytical relationship between work and power.